So for today, why don't we go over the Arrhenius equation? And with this equation, we can actually calculate the E sub A, which is the activation energy, or the frequency factor, which is the letter A. So let's dissect this equation just a teensy bit. So K is basically your rate, right? The little k. A is your frequency factor. R is the gas constant, which is the 8.314 joule per mole K. And temperature, this has to be in Kelvin, right? Because this is in Kelvin. And when we calculate it and we figure out our activation energy, what unit is that going to be in? That's going to be in joules. Right? Because the energy is joule per mole K. A is just a constant. So they break it down and tell us that, let's go down to this square here. If you were to graph the ln of K, so the rate constant, the natural log of the rate constant versus 1 over the temperature in Kelvin, if you were to graph it, you would see that the slope, m, is negative E sub A over R. So if you're given, for example, a set of data like this, you could graph it and then you would be able to calculate the slope, and then you would multiply whatever number you got for the slope by 8.314 and then take the negative of it, and that's the E sub A. So, that being said, they give us an equation that does just that. The ln of any k sub 1 over k sub 2 minus, or times the activation energy divided by the gas constant times 1 over T2 minus 1 over T1. So you notice that you could pick any pair for K2 and K2 as long as these, it's the one that's on the bottom of this fraction and in the front here, and K1 just has to be the top one here and the bottom one here. So just as long as you keep them straight. So for this situation, I'm going to do number 14.63. And what it says is calculate, so let's back up a second. I could give you a problem and tell you that they graphed the ln of K versus 1 over T, and the slope was this number. What's the activation energy? So that's what we just went over. If I gave you the slope was negative 0.1, you would multiply the negative 0.1 by 8.314 and then take the negative of it and you get E sub A. So that's the easy, quick one. This one, however, I give you a set of data and then you have to calculate the E sub A for the above data. Well, here's the trick. So it tells you in this problem in 14.63 that you have to graph it. Is that exactly true? No, because if we remember our back in the day, what does slope equal? M equals y1 minus y2 over x1 minus x2, right? So to find slope, you don't need any more than just 2 points. So the same is here. So we could just pick this first one and this second point to find the slope, because the slope is going to be the same throughout all the data. So let me pull up my calculator here. What is the issue with the temperatures that are given? They're in Celsius. So I have to do 15 plus 273. I'm going to say that it's really 288 Kelvin. And for 25 plus 273, that's our 298. We're pretty used to that number. Kelvin. Okay, so I'm just going to compare these points. So I may call this my 1 and this one's going to be called my 2. So when I plug it into this equation, I'll make sure that I plug the 288 in for T1 and the 0.0521 in for K1. How's that sound? So let's go ahead and plug these in down here. There's actually a couple different ways we could do it, but using that integrated, equation is probably the easiest. So it's going to be ln of And like I said, K1, which is my 288, divided by 298 equals my E sub A, which is my unknown, divided by my R, which in this case is the 8.314. Remember, there's a couple different gas constants, so make sure you use the correct one. Times 1 over, and my T1 is 288, minus 1 over, oh, I'm sorry, it's 1 over T2. Sorry, see, I make mistakes. 298 minus 1 over 288, because this has to be my T1, T2. Okay, so these are going to be teensy numbers, aren't they? 1 over 298. So I'm going to go ahead and calculate 1 divided by 298, and then I'm going to subtract from that and put in parentheses 1 divided by 288. I got negative 1.165 times 10 to the negative 4. So that's eensy weensy numbers, right? And then my E sub A over 8.314. And that's going to equal the ln of 288 divided by 298, so it's the ln of 0.96644. Let me see if I have that function on here. I do. So, moving my messy, sloppy work up here, I get negative 0.03413 is equal to, so in order to get this into one constant, what I could do is take negative 1.165 times 10 to the negative 4 and divide it by 8.314. Oh, hold on. I'm doing this with a computer. Scientific calculator, which is not exactly the most. So I'm going to divide it by 8.314. Okay, so I get my E sub A is times 1.14 negative 1.401 times 10 to the negative 5. Okay. And it's a negative, right? Negative number, because this is negative. And this is negative now. So I can ignore the negatives now. So essentially I'm going to take 0.03413 and divide it by that small number, right? So 0.03413 divided by, put that in parentheses, 1.401 times 10 to the negative 5. And I get, and remember it's a positive number now because these negatives cancel out. I get my E sub A is equal to 2436. And so that's actually in joules, right? So if they ask for the E sub A in kilojoules, you would say E sub A equals 2,000, or 2.4, I'd say 2.44 kilojoules. So that's how you calculate E sub A. I hope this helped. If you have to calculate A, let's do that super quick. Why don't we just do that for, I was not planning on it, but let's go off the rails here for a second. If we wanted to calculate A now, the easiest place to do that would be this first equation, right? So you could pick any trial you'd like. Use that K, use that T, because those are the things that change with the trials. So find the K, find the T. So let's use, how about data point number 2? So 298 is our T, and 0.101. So if 298 equals T and 0.101 molarity per molarity per second equals little k, right? And we also know that E sub A, sorry, this is all, off the rails here. We know that E sub A equals 2436 joules. So we can now just plug into this equation. Why did I put it back in joules? Because my R is in joules. So the E sub A has to be in joules. So the answer for this one would be 0.101 equals my unknown A, and then E to the power of negative, and then this will all be a fraction, right? 2436 divided by 8.314 times 298. Okay, so we probably should clean this mess up real quick. So 2936 divided by 8.314, and then we're going to divide that again by 298. We get A times E to the power of negative 1.85. 1.185. I'm going to sneak that one in there. And going to get that number, and I got 0.101 equals A times 2.718. Oh, let me see if I can get this correct. Let me double check. All right, so I did make a disclaimer that I'm working with a calculator that I'm not super familiar with. So I knew that that was wrong. So e to the power of negative 1.185. So it's actually 0.101 equals A times, and the real number is 0.3057. So then to solve for A, we just divide 0.101 divide by that. And we get A equals 0.331. And what are the units for A? There are no units, so that's actually the answer. So if we actually wanted to write this expression in its entirety, with all the data that we're given, we would say that K, little k, equals 0.331 times E to the power of negative 2436 divided by RT. We could even simplify the this number here and put a negative number divided by t, but this is the expression since the only unknowns and the only things that change with temperature or with different temperature are the k and the t. So, so that's how you can determine. And we basically broke down the Arrhenius equation to figure out how to calculate activation energy. We paralleled it with our graph, and we discovered that you actually don't have to graph it out. You just need two different rate constants at two different temperatures, convert them into Kelvin, and then you're able to plug them into this equation, which is very similar to the y equals mx plus b equation. So I hope that this helped, and good luck, everyone. Thanks.